Hello, and welcome back to Topic 4, Applications of Derivatives in AP Calculus AB. Today we are getting our really first look at the most common free response style question in the history of the AP Calculus exam. This question type has appeared on every single AP exam since 1969. It's a long time. The general idea is they will give you the graph of f prime of x. They're going to say, cool, here's the graph, not the equation. The equation will almost never be given to you. They're going to give you the graph and say, okay, here's the graph. What can you tell us about f? Can you tell us where f has points of inflection, where f has relative maxes and mins, where f is increasing, decreasing, all that fun stuff. Sometimes they might give you a table for f prime. In fact, they will probably give you a table for f prime, but usually that's a different style question. That tends to be more of a real-world problem, and we'll see more of those as we go through. But this is here's the graph of f prime, now tell us stuff. Sometimes it's calculator active, and in fact you're going to use a calculator on these first two problems, so please get your graphing calculator out. Other times though, it might not be calculator active and they just give you the graph, and so you need to be good with both. So what are we trying to do here? Well, we are going to, without graphing the original equation, do a few things. First, we're going to create the graph of the derivative on your calculator. Second, we're going to use the graph of f prime, which is the derivative, right, to create a sign chart for f prime. And then last but not least, we're going to use the graph of f double prime to include f double prime in our sign chart. Then we're going to graph the original equation and make sure our sign charts match up. And it really might help you to have your day 44 organizer out for this too, that third page where we talked about if f looks like this, then here's what f prime and f double prime look like. But let's go ahead and get started. So I imagine you might not know how to graph the derivative because, oh yeah, I've never showed you yet. So we should probably do that. I'm going to show you how to do this on two different calculators, on the Inspire and on the 8384. And the reason I'll show you both is because people are still using both. If you have a Casio or an HP or something, then that's not going to be in this video, but you can reach out separately and I'd be happy to help you out. So let's start with the x cubed minus 6x squared plus 9, and I'll go ahead and be bold and do that one on the 84 first. I think we can see both. So 84, usually turn it on, starts at your home screen. You want to hit the y equals, and you want to make sure everything's cleared out. So I'm going to go ahead and do that. X, and notice I use this key for x. This is probably the better one to use for x than the x that's hiding down here where you have to do alpha than that, because this one changes depending on which mode calculator you're in. But either way, x cubed, right, minus 6x squared plus 9, and I wish I knew how to do a squared. There we go, plus 9. If your calculator doesn't do the cube up here and instead actually writes the caret, then either you're using an 83, mine's an 84, and yours will never do that, or you're using an old version of the 84 that doesn't have your operating system, your OS, updated. Your operating system, second memory about, should say 2.55. That's the last operating system for the TI-84 Plus. If you have those new ones, the CEs, the cool color ones, your operating system's different. But if yours doesn't say 2.55, then you have an old operating system and you should go to your teacher so that they can update it for you. It's really useful to be able to have this extra math type where you can do that. You can do alpha, y equals, and do fractions, all that fun stuff. So make sure that you do have that updated operating system. Okay, I'm not going to graph this though. In fact, I don't even want to see the graph, so I'm going to go left and turn the graph off. Okay, next up, I'm going to go to the next line, and I want to graph the derivative of this equation. And the quickest way to graph the derivative of this equation is to use the derivative button on your calculator. So math, and then we're going to go down to, I think it's 8. Yeah, math 8. I want to do the derivative, and again, if you have the newer operating system, this will pop up. If you have an 83, reach out to me because it's a little bit different syntax. dd what? Well, I want to take the derivative of this whole equation, and think of this equation as y equals all of this. We want to do ddx of Well, you could retype this equation over here, but we've already typed it once. Wouldn't it be easier just to copy it down? And we can do that, right? If you go alpha F4, you have a list of all the different y's. This equation up here is called y1, so I want to copy y1. But then this part's weird, because when we've done the derivative of an equation at a point before, we've always put a number here. So we could calculate this derivative at x equals 2, or x equals 5, or whatnot, but I don't want to do just a single point. I want to calculate or graph the derivative calculations at every x value. So we're going to graph this derivative at x equals x. So that's just going to tell the calculator, change x, and as it changes x, it calculates new derivatives. And then a graph. Okay, it's going to look something like this. Very exciting. And you'll notice it goes very slowly, right? The processing speed on these 84s is much slower than the Inspire, so it definitely takes a while to do that. Now, the shape of the graph shouldn't shock you, right? This original graph was x cubed. The derivative of x cubed is x squared, so we make a parabola. Nifty. All right. You can, if you don't have an 84, you can skim this next part because I'm going to show the Inspire. However, you might want to set up the graph of cosine squared x squared, how I do the Inspire. So actually, maybe you should pay attention. So next thing I'm going to do, there are a few ways to do this, and I will probably show you just the same way there so we can understand the similarity. So I always hit this calculator button to switch back and forth between our calculate screen and our graph screen, right? If you start at the home screen, you have calculate graph. I would suggest you should not use these down at the bottom. It fills up your memory really quickly. Instead, just stick with the calculate graph, and you can just use this to go back and forth. So graphing screen. If there's anything in here, tab down so you don't see it. Delete 3 times, yes, tab again, you're back up. Cool. We want to graph this cosine squared of x squared, and in fact, there are very few, if any, calculators that can actually graph that. And this throws off my students. This has definitely been included in calculator active problems before. My students are like, well, how do you graph that? My calculator won't let me do it. Well, we need to remember that trig notation is supposed to be shorthand, and what it really means is cosine of x squared, all of that squared. It's cosine of x squared times itself. So we do need to rewrite it with the square on the outside of the parentheses. And that's true for the 84 as well, so be careful there. So let's go ahead and do that. So we have cosine of x squared, all of this squared. And you have to be very careful with those parentheses. If you throw it on the inside, you won't be squaring the right thing. But I don't want to graph this, and so actually if I hit enter, or if I go down, if I hit enter, it goes away and it has the graph. I'm like, ugh, I don't want that at all. So what I'm going to need to do here then is go up to my history menu, and actually I should do it without clicking the mouse, sorry. I'm going to hit tab. If it does that, it's because your cursor is over the graph, so just click somewhere else, hit tab, brings you back up here, and then you can just hit the up arrow, and if you want, you can go to the far left. Takes a little bit, and you can hit enter on the checkbox. You can also run your finger over the scroll pad till you get there, click on the checkbox. Very exciting. Okay, now when I hit enter, there's no graph. It's still there, but no graph. Cool. Please notice that this graph is named f1 of x. It's bolded because we've defined that as the name. So when I go down here, I want to graph the derivative of that. And this derivative is a little bit different. Strangely, this derivative is hiding next to the 9. I call this the quick key or the shortcut key button because you might notice if you choose this button to the right of the 9, it pulls up a whole bunch of common shortcuts, right? Fractions, exponents, absolute value, all that fun stuff. And the one we're looking for is this dd something of something. Now this will only work on the graphing screen unless you have this CAS, this CAS, then it'll work anywhere. But for regular calculators, it'll only work on the graphing screen. I'm going to hit enter on it and it says dd what of what? Well, ddx, same as we did on the 84, of what? Well, remember, the equation name, let me go back up. And it deleted it, cool. The equation name is f1 of x, so that's what I'm going to use. Quick key. It remembers where I was before. That's very useful. ddx of, and I'm going to type in f. Notice it's not bold, but as soon as I hit the 1, changes to bold because that's a defined name, f1 of x. Hit enter, and bam, we have this. Now, this looks intimidating, right? It goes up forever and ever. That's very, very weird. I don't like it. Luckily, though, we're only looking from negative pi over 2 to pi over 2. So let's change my window. Menu, window. Window Settings, and we're going from negative, and you can actually type out the word pi, but there's also a pi button down here. We want to go from negative pi over 2 all the way up to pi over 2. And I'm going to leave the scale to auto for now. I think there's no reason for us to choose an actual scale. Hit enter, and we've got this nice graph. Woo! Very exciting. Technically, we're going from -2 to 6 on this guy as well, so I might as well change that. In fact, this doesn't look like a standard window to me, so why don't I do zoom and then standard. Oh, it's going to take 50 years. I should have changed the window before, but that's okay. We're getting there. Look at this. Woof. Okay. We're going to go -2, which is over here, to 6, but I think we're actually off the screen down here, so I'm going to try to go from like -20 to 20. So window, we'll go -2 to 6. And then y-axis, let's go -20 to 20. And we can let it scale. It says scale by 1. If we're going to 20s, let's scale at least by 2s and see what happens. And then graph. -2. Oh, I still can't even see the top of the graph over there because it starts up here, goes down. At least we got the bottom part, and then goes somewhere over there. Yeah, either way, that's pretty good. We might need those endpoints at some point, but not a big deal. Alrighty. Sign chart time. We ready? We're going to make a sign chart from this graph of f prime. So my sign chart here then needs to include f prime. And I'm going to keep my keyboard attached, so things are going to look a little bit strange because it's hard to write with the keyboard on here, but I think you'll be okay. Sign chart, we need to leave space for both f prime and f double prime. Okay, you can use this to help guide you. Okay, we're going to start with f prime. I'll do that one in purple. Eventually we'll need f double prime. Okay, f prime of x, we're going from -2 over to 6. What goes on the f prime sign chart? Well, critical points go on there. So let's go ahead and pull up this piece over here. Critical points, critical points, critical points. Well, you might be tempted to say that this piece down here, this relative min, is a critical point, but it's not. Because critical points occur when f prime, or you could think when the graph of f prime equals 0 or is undefined. Undefined, there's no gaps here, this is just a parabola, but equals 0, where a graph equals 0, the zeros, aren't those just a fancy word for the x-intercepts? So we have, it looks like 2 zeros here. And looking at these zeros, right, I think we can probably see that this is 0 and then 1, 2, 3, 4. If you wanted to be sure, and I'm always suspect of parabolas, I think that's 4, but if I wanted to be sure, don't forget you can do second calculate 0, and then you've got this little cursor over here, so I'm going to move the cursor pretty close, but it says left bound. So as soon as I get to kind of right about there, I want to hit the left arrow for a bit and go to the left. I want to bound this intercept on the left side. Hit enter, and you'll notice there's a little triangle that appears up above, and it says, okay, that's the start of the interval where you think there's an x-intercept. Then I went somewhere to the right, doesn't matter how far. Hit enter, and you'll get a second one. So it says, do you want us to guess at the, which is a bad word, it's really calculate, but do you want us to calculate or find the y-intercept that lies between these two triangles? Well, yes, I do. So I'm going to hit enter a third time, and it says, okay, we think it's 3.9999999, and that's because the 84's guessing skills aren't awesome. They're okay, though, and we need to realize that that does mean exactly 4. So it looks to me like I have 2 x-intercepts, and it says y equals 0, but this is the graph of f prime, so this means f prime equals 0, critical point. So 2 critical points on here. One of them is at 0, and that's where f prime becomes 0, and the other one is at 4, and that's where f prime also becomes 0. But the rest of the sign chart that we want to fill in are actual values in here. Now there's 2 ways that we could find these values, and I want to show you both of them. I think they're important. This graph is created by y2. We see that down there, right? And so if I wanted to find a value between -2 and 0, our normal process would be, well, we'd say, let's see, 1's in there, isn't it? So you'd probably find f prime of 1, which means you'd need the equation and you'd plug 1 in. But we never actually found the equation by hand. But our calculator is super cool, so let's make it do it for us. Let's find f prime of 1 using the calculator. So I'm going to do second quit, go back to the home screen, right? And by the way, if you're watching this, it probably is good to watch this, and then you're going to do the same thing on the Inspire if you have an Inspire and not an 84, vice versa. So you'll do both of these, but watching this isn't going to hurt you. So f prime of 1. So I went back to my main home screen, my calculation screen. I want to plug 1 into f prime, but the equation f prime has a name. It is y2. So what I'm going to do is alpha f4, and I'm going to call up y2. I want to say use y2, and we want to evaluate that at 1. So we're going to use function notation, y2 of 1, and hit enter. Ha! Negative 8.99999. That's just negative 9. So f prime of 1 is negative 9. Oh, I put 1. Well, that was really silly. I guess 1's over here, isn't it? Awkward. F prime of 1 is negative 9. So we know that this interval is negative. However, that was actually too much work because we have the graph. And the graph, it's so easy to tell the values of f prime. F prime of 1 was negative 9, that's right down here, but I know that. The graph is below the x-axis. So actually from 0 all the way over to 4, the graph of f prime is below the x-axis, which means the graph of f prime is negative. And so why would we bother plugging anything in? Above the x-axis on these two sides means f prime is positive. And in fact, that's where your organizer from day 44 might come in handy. Right? We know that f prime is positive when f prime is above the x-axis. Okay, let's go ahead and do the same thing with our second one, but we'll do a little bit faster. So I have this one over here. I want to find my critical points first. I imagine that hopefully we remember that these two are not critical points. They might look like it because you're like, that's where the slope is 0. No, it's not. This is the graph of f prime. F prime is the slope, and when f prime is equal to 0, those are zeros or x-intercepts. 1, 2, 3, right? Nothing too bad here. So we have 3 critical points. Those are the x-intercepts, and I'm going to go ahead and find them. I'm going to be a little clever too. This is 0. Doesn't this look like some symmetry though? To me, this looks exactly like this, but flipped and flipped. So my guess is whatever this is the same value but positive. So let's just find one of them. Menu, and if you're on the 84, you should be using your zeros, but I'm going to analyze the graph on the Inspire, and then 0. We need to run your finger over the mouse or tap the right arrow. I'm just going to do the one over here. We need to click somewhere. We need to click the little clicky button over here. Somewhere to the left, it says lower bound, to the left of the 0. Click a second time to the right, and it says the 0 is exactly 1.25. But I do not believe that, so I'm going to go ahead and hit the plus button on my keyboard over here, right? There we go. On the keypad, I guess. And it is not exactly 1.25, it's 1.2533, whatever. So 1.253, and I'm going to quickly record that in my sign chart, which does not yet exist over here. So, second sign chart, something like this. Negative pi over 2 to pi over 2. Split that in half as best we can. We have f prime of x. There are 3 critical points. One's at 0. Okay, 1 was at 1.253-ish, and the last one is going to be the negative version of that. You should not assume, like I did on the AP exam. Please actually find all 3 of them. You just repeat the process again to find the zeros, but for this one I'm pretty convinced. And then what about the signs of f prime? Well, 2 ways to do it. One way is you can plug in a value. Let's just do between 0 and 1. I'll do this guy right here. And I think between 0 and 1.25 we could just use 1, just like we did before. So if I wanted to substitute 1 into this graph is called f2 of x. So I'm going to hit my switchy button. We'll go back here, and I want to find f2, notice it's bold, of. So I want to evaluate my derivative at what value of, I think we said 1, didn't we? Enter. And it gave me that. Silly exact mode. Didn't want to round, how rude. So control approximately negative 1.818. So when I tried 1 into the derivative, I got a negative, but we should have already known that because we have the graph of the derivative. And at 1, somewhere in here, the entire graph of the derivative, f prime right here, is below the x-axis. Below, above, below, above. Negative, positive, and so we can fill this in. Negative, positive, negative, positive. Cool. this actually gives us a good indication of what my original graph looks like, right? It tells us my original graph will increase and then decrease and then increase. And this original graph will decrease, increase, decrease, increase. All right, well, let's look at f double prime. It shouldn't shock you that the process for f double prime is not too different. It is slightly different on the Inspire versus the 84, just because the 84 is older. So if I want to do this derivative, then I'm going to go down and I'm going to turn this guy off, still leaving it here. We might use it later. And I'm going to go down to the third one. So if I want to find the second derivative, that's the derivative of the first derivative. So same process. Menu, 8. ddx of what? I want to do ddx of the first derivative, so ddx of y1. Nope, y2, sorry. Of the first derivative, evaluated at x equals x. Now this is going to take an age or two to graph, because what the calculator will do is first it will graph the derivative of y1, and then it will graph the derivative of y2. And when I say graph, it doesn't actually know what the graph looks like. It literally graphs this first equation and then finds the slope between 2 points, lots and lots and lots and lots of sets of 2 points, and then graphs all those slopes. And then to graph y3, it's going to find all the different slopes of y2 and then graph those. So this will take some time. In fact, I'm going to let that just kind of creep up for a bit. We'll come back to you later. And we're going to do the same thing over here, but it's a little faster on our newer Inspire. So I'm going to go up, I'm going to turn this one off, we're going to go down, and this one, in the quick key, we actually have a second derivative button. So I'm just going to graph the second derivative. Now it's a little bit different here. I don't want to graph the second derivative of f2. That would be the third derivative. I want to graph the second derivative of my original equation, f1 of x. And when I graph that, look how quick and easy that was. So exciting. Oof. This one's pretty wild too. Look at all the different x-intercepts over here. And this one actually crosses so close to pi over 2 that I'm going to change my axes a bit, because otherwise we might think that's outside the interval. So I'm going to go ahead and do window zoom, window settings, and I'm going to do negative pi over 2. I'm going to go one more negative just by putting a -1, and pi over 2, I'll just go one more positive. I think that should be enough. Oh my gosh, things are just crazy here, aren't they now? Look at all of those. So I have a bunch of zeros on my plate. Luckily, there's symmetry over here, and it might also help us to know what pi over 2 is as a value. I might have mentioned that you can type out pi over 2, so I'm going to do that quickly. Pi over 2 approximated is the value 1.57. So once we get past 1.57, we're done. Let's go ahead and find all of those zeros over here. So, menu, analyze graph, we're going to find a 0. We'll do this one first. Boop, boop. There's that first guy. Okay, then, and I want this to go away, so I'm just hit delete on it a couple times. Go away. I said go away. There we go. Okay, we'll do this a few more times. So, menu, analyze graph, 0, menu 6.1. You'll get pretty used to that, I think. 1.55, I don't trust it. There we go. A few more, looks pretty good. Let's do another one. 1.55 though. What was pi over 2? Oh, my brain is not working. Pi over 2 is 1.57. Oh, cool. I bet I just need to go one more over here and I should be done. Let's double check. Menu, analyze graph. Woof. There we go. And we have our last 0. Yeah, that's too big. So we're not going to use that guy at all. And I would like you to go away by hitting delete. Thank you. Cool. So we really just have 0, this guy, and this guy. So it looks like just 3 on this side, and then of course the same 3 on the other side. Not 3, I'm sorry, just 2. 2 on this side, and then this one was too far. Okay, so 0.958 and 1.551. So now I'm actually going to cheat and use this down here. So, and we have a lot of these. Negative 1.558 is where this became 0. The next one is negative 0.958. That fits in here. Negative 0.958 is where this became 0. 0 becomes 0. And then the same ones through symmetry on the other side. So 0.958. Okay, and then the last one is 1.558. Over here. Oh, look at all those potential inflection points. I can't call them inflection points until we decide that f double prime changes sign. Let's do that, just above and below, right? So f double prime, let's see, here is 1, 2. Okay, so to the left of that, it looks like f double prime is below the x-axis, so it looks like below, above, below. So below, above, below. Same thing that we did for f prime. We're just checking the location of the graph. And then we work the other one, below, above, below. So below, above, below. All right, well, what does this look like then? If we go through, I'll use the green to show the original graph, concave down, concave up, concave down, concave up, concave down. And so if this asked you to identify the inflection and critical points, well, critical points, easy. Critical point, critical point, critical point, because that's where f prime is 0. Inflection points, a little harder. Inflection point, not an inflection point, inflection, inflection. Because inflection points have that additional burden of proof where not only is f double prime 0, because f double prime is 0 at all 5 of these, f double prime has to change sign, and it didn't change sign here, therefore not an inflection point. Okay, so not too bad here. Let's go ahead and look at the other one, which I think was a much more simple graph. Come back to us. There it is. Much more simple graph, crosses the x-axis at 2. I'm going to make a bold decision and say that's 2 right there. And we are below, before, above, after. So we are at 2 down here, below, before, above, after. So concave down, concave up. Nice. We were able to learn all of this about the original graph f without graphing f. And that is pretty cool, right? We have a good idea of the shape of f without having this, right? And so this is what's going to happen on pretty much every problem. They are going to give you the graph of the derivative, not the original graph, the graph of the derivative, and you're going to have to determine features of f. We know that f is increasing, decreasing, increasing on those intervals. We know that f is concave down, concave up. We know the inflection points, the critical points, all without ever looking at or even using the graph of f. I know I did have to use the graph of f to actually do the rest of these, but let's just double check this first one and make sure we didn't make any mistakes, because I can have these up at the same time. So we're going to go ahead and turn off this derivative. We don't need to spend 10 years waiting for it to graph again. I'm going to graph the original equation on the same interval, and look at that. Let's check the increasing, decreasing first. Does it increase until 0? Yep. Decrease until 4? Yep. Increase after? Cool. Are we concave down until 2-ish? Yep. And then concave up after? Yeah, that looks really good as well. Nice job. All right. So the bottom of this has you fill in a few things, right? And you can fill those in, I think, on your own. They're nothing too terrible. However, part F probably needs some explaining, so why don't you pause me, fill in A through E. If you get stuck on any, you can totally ask, but it's really just a summary of what we just did, and then we're going to talk F. All right, hopefully you had a chance to get through all those. Let's go ahead and discuss F. Explain 2 different ways you could determine where F is concave up and concave down. One explanation should use F prime, and one should use F double prime. Well, let's use the F prime one first. No, I'm sorry, let's do F double prime first. F double prime is pretty easy. If you wanted to use the graph of F double prime of x, right, to find concave up or concave down, concave up is F double prime is above the x-axis, right? And of course, concave down is F double prime is below the x-axis. And that would be great. If you had the graph of F double prime, super cool. But one thing the AP exam is pretty picky about is if they don't give you that graph, they don't want you using that justification. So if you said, I think F is, or I know F is concave up from 2 to 4, and then you had to justify. So you said because the graph of f double prime is below the x-axis, but they only gave you the graph of f prime, then they probably wouldn't accept that as an explanation. So if we just have the graph of f prime, how can we see this? Do you remember? Well, we need to remember that f double prime describes the slopes of f prime. So the other way we could do this is if you had the graph of f prime of x, right? If f prime of x is increasing, that's positive slopes, that, and actually I should have done this backwards, sorry. Your graph of f will be concave up if f prime of x is increasing, right? That's where your slopes are going up. And your graph of f will be concave down where f prime of x is decreasing, getting ahead of myself in letters, is decreasing, which means going down. And we'll see that again in just a bit. All right, so I think at this point, we're going to go ahead and actually start looking at a couple free response questions. There is a nice practice on this page, but we're going to skip it. And in fact, in the next few years, you probably won't even see that there. And we're going to get right over to this question. So I have three free response questions, I think. This one's all the way back from 1996, predates most of your births, I think. Predates me being in high school, actually. So this is from 1996. It's a free response question with amendments. I've added a few things. Don't worry, I had a majority vote. You're fine. It's election year humor. So let's go ahead and see what we need to do. The figure above shows the graph of f prime. Well, if it shows the graph of f prime, then any time we're asked for justification, we better reference the graph of f prime. Even if you're talking concavity, we don't have the graph of f double prime. We're not going to use that in our justification. And some people say, well, wait, couldn't I figure out what the graph of f double prime looks like and draw it? And the answer is yes, but they still won't like it. Stick with what they give you for justification. All right. The domain is a set of all real numbers such that x is between -3 and 5. Okay. For what values of x does f have a relative maximum, and why? Well, what I'm actually going to do is make a nice little sign chart here. And so when I make this sign chart, I always like to kind of set it up equal to these axes, right? Something like this. And it kind of gets a little messy here. I wish I had a little bit more space, but that's okay. I'm going to split this into two pieces, hopefully better than that. Something like this. There we go. And we're going to look at the signs of f prime and, of course, the signs of let's not use that color. The signs of f double prime. All right. Well, let's start with the signs of f prime, because the easiest way to determine where f has relative maxes and mins are to look at what f prime is doing. This is the graph of f prime. Let's start with the critical points. The critical points occur where f prime is 0. This is the graph of f prime. A graph is 0 at its zeros, at its x-intercepts. So we need to find the x-intercepts of f prime, which are right here. And you might notice that I'm not putting the labels on there. I am going to put the labels, but you could also just use this as your labels down below. So, and it just gets messy. So this is going to be -2, this is 1, and this is 4. We found the critical points, great. But to find increasing, decreasing with our first derivative, the first derivative test, we need to test various points in the intervals, or, shortcut, we have the graph. F prime of x is greater than 0 here because it's above the x-axis, which means f prime is positive. Then f prime is negative, f prime stays negative, f prime goes positive. So negative, negative, positive. Therefore, if I wanted to sketch the original graph, and I'm going to do f of x in blue, we know f of x will increase and then decrease. Whoops, I didn't do that one well. It will decrease all the way across here and then increase at the end. For what values of x does f have a relative max? I want to see one relative max. I see that right there, don't I? So let's go ahead and explain. At x equals -2, f has a relative max because, read your sign chart, you'll be just fine. What happens at -2? F prime changes from positive to negative because f prime changes from positive to negative. Great. All right, why don't you try that justification for a relative min? We've already done all the work for it, so it shouldn't be too terrible. And then we'll check in with me and see how you did. Okay, hopefully you got that 4 was the relative min, right? At x equals 4, f has a relative min because f prime changes from negative to positive. All right, next up, on what intervals is the graph of f concave up? Use f prime to justify your answer. Even if they didn't say use f prime, you are expected to use f prime because that's the graph that they gave you. So how do we see concavity from this graph? Well, don't forget that the second derivative is the derivative of the first derivative, and a single derivative always describes the slopes of the equation of which it took the derivative. So f double prime is going to not only tell us concavity, it's going to describe the slopes of f prime. So let's look at the slopes of f prime. F prime is decreasing negative slopes until negative 1. At negative 1, there is a slope of 0, slope of 0, slope of 0. To me, it seems like there are 3 spots where f double prime will be 0, and that is where the slope of f prime is 0. In terms of the signs, well, we said f prime is decreasing until there, so that is a negative slope, then increasing, positive slope, then decreasing, and then increasing. And that is quite tricky. If we had the graph of f, if this was the graph of f, we would probably say that we are concave down, concave up, concave down, concave up, concave down, concave up, concave down. But this is not the graph of f. We cannot see the concavity visually. We have to look at the slopes of f prime. And man, is that tricky for people. So don't feel bad if you're like, I'm not quite getting it yet. We will practice. Use that day 44 tracker or organizer to really help you out. Okay, now we said f double prime is negative, positive, which does describe the slopes of f prime, but it also describes the concavity of f. So this is concave down, concave up, concave down, concave up. All right, well, I think we can see our concave up intervals, can't we? We went from, this is negative 1, 1, and 3. It looks like it goes from negative 3, right, that's over here, to negative 1 is concave down, concave up, concave down to 5. So let's at least put the intervals over here. Again, the intervals don't matter, open or closed, your choice. So we would say f is concave up on what intervals here? Concave up from negative 1 to 1 and 3 to 5. Negative 1 to 1 and 3 to 5 because, and this is the tough justification, real tough. We're not going to say because f double prime is positive. How did we know f double prime was positive? We knew f double prime was positive because f prime is increasing. Right? That's where we need to use f prime to justify. So I went back to the graph. So because f prime of x is increasing on those intervals. You could go further too, and you could say that f double prime is the derivative of f prime, and so because f prime is increasing, f double prime is positive. That's fine, but this should really be clear enough, right? F is concave up because f prime is increasing. We have to use f prime. All right, part D. Suppose that f of 1 is 0. Okay, well, we might as well graph that. F of 1 is 0. Cool. In the xy plane provided to the right, already got there, draw a sketch that shows the general shape of the graph of function f on the open interval. So we want to draw f. Well, we're only going from 0 to 2, so I can highlight this, I think, pretty easily here. We're going from 0 to 2. So here's what I need to cover. Let's start with f prime. F prime shows us our graph of f decreases, though it does have a slope of 0 there. We'll get a slope of 0 in just a second, I think. We know this needs to, it doesn't tell us where it starts, does it? So it just needs to go through there. So we have to decrease until here. and we'll get a slope of 0 in just a second, no stress. Then we also have to be concave up for this first part and concave down for the second. It switches concavity, inflection point, it looks like, at 1. So let's give this concave up. It's got to look something like this. And then concave down looks something like this. And so if I erase this, it looks pretty darn good. Now, it did say there was a slope of 0 here, and so that slope of 0 is probably coming for this going perfectly flat and then dropping down after, kind of like that cubic function. So there is a horizontal tangent here, right? It's created by a slope of 0 at 1, and I think that's totally fine. That's all we can do. All right. Find the inflection points for f on that interval. Okay, inflection points, things get a little trickier. We need to remember inflection points are not just where f double prime is 0, but they can be. We also need to make sure that f double prime changes sign. So on either side of this first possible inflection point, does f double prime change sign? And yes, it does. Change sign, yep, negative to positive to negative, and here's negative to positive. It looks like it does, f double prime does change sign. So there are 3 inflection points, -1, 1, and 3. So f has POI is a very common point of inflection, right? Inflection points at x equals -1, 1, and 3 because, well, we can't say f double prime changes sign here because we don't have f double prime. So what changes about f prime at those spots? Well, one thing you might be tempted to say is that f prime has horizontal tangents, or f prime equals, or the slope of f prime is 0 here, but that's not enough. We have to talk about what happens on each side. So f prime is decreasing on the left side, increasing on the right. We changed from decreasing to increasing. Same thing over here, we changed from increasing to decreasing, or over here we changed from decreasing to increasing. So we need to somehow say that succinctly, because I don't want to write forever. So I would say something like, because f prime of x changes from increasing to decreasing, or vice versa, at, and you could say those points, you could rewrite it again, you might not even have to rewrite it, but better safe than sorry, and that would be fine. Whew. All right, well, part F is a fun one. Create another question about the graph of f prime that could be a good AP style question. You could talk about where are their critical points. A really good one and a common one is maybe where is f both decreasing and concave down? Or, some combo where you have to look at both of them at the same time. Either way, go ahead and create one, see what you can come up with, and I'm excited to check those next class. And then once you're done, we'll move on to the last page. Alrighty, here is our last page. There are 2 more questions here. Question 4 from 2003, that might have actually been around when you guys were born, and then 2004 might get the rest of you guys, or if you're quite young, we're still not there yet. And so we have these 2 questions, both giving you the graph of f prime, the most consistently common question on the AP exam. I wish you the best. Once you're done, you can unpause and I'll talk you through them. Alrighty, here we go. I see this, I see increasing, I see points of inflection. Before I even attack those, I'm making a double sign chart. So let's see, I'm going to go up here, go up here. Okay, so here is my double sign chart. I'm just going to use the top of the paper, the top of the graph. Oof, this is a rough one for me. Okay, today is the day of wavy lines. Oh well, I give up. Cool, and we'll split this in half like so. And we have our, I should just zoom in over here, probably should have done that at the beginning, f prime and f double prime. We are starting at -3, we are going over to 4. Looking at the graph of f prime, which is, as a reminder, the one that's in blue right here, right, this is the graph of f prime. I want to find critical points first. Critical points occur when f prime is 0 or undefined. This is not undefined anywhere. It would be undefined if there was a gap, but if this is continuous, f prime is defined everywhere. However, f prime is 0 in a few places. I see an x-intercept here and here. So -2 and 2. Cool. What about the signs of f prime? Well, f prime is positive when f prime is above the x-axis, so positive. Below the x-axis, below the x-axis, negative, negative. So what is my graph of my original function? I'll do this one in red. What does that look like? My original function will increase, then decrease, then increase. All right, on to f double prime. And this is the part that takes the longest. Once you have your sign chart set up, answering the questions is really easy. So, f double prime. F double prime is the derivative of f prime. It describes the slopes of f prime. So f prime is decreasing until this guy, right? Decreasing until there. Okay, so this is -2. Oh, that's nice. I'll leave this blank, but we are decreasing until there. And then we increase until 2. Oh, wait, sorry. This is 0, isn't it? Oh, man. Crushing it today. So this is 0. We decrease until an x of 0. So, like so, we decrease. And then from 0 to 2, we increase. And then from 2 to 4, we decrease. Now you might notice that I left these two signs in here blank, and I did that because we need to be careful here. The slope of f prime, fit a horizontal tangent, it's smooth, it's flat, is certainly 0 here. But what is the slope down here? Oh, that's a sharp point. And that means that there is a spot where f double prime does not exist. And I think it's always very important to keep reminding you of the differences between a slope of 0 and a non-differentiable point where the slope doesn't exist. Okay, we have all this. We know we are concave down, up, down. Let's go ahead then and answer our questions. On what intervals, if any, is f increasing? Ha! I've got a sign chart. I'm going to win this. So f is increasing. So f is increasing on, where is f increasing? Oops, I did my sign chart wrong. I'm so sorry. Those are both negatives. We are decreasing all the way through. Woof! Apparently I should get some sleep. So f is increasing, and it looks like just going up from -3 to -2 because f prime of x is positive. You could also put f prime of x is greater than 0, whatever sounds good to you. Find the x-coordinate of each point of inflection on the graph of f on the open interval. Justify your answers. All right, x-coordinate of each point of inflection. Well, first, does f double prime change at each of these potential points of inflection? It does. That's always very nice. So I see 2 points of inflection here, right? So we'd say f has points of inflection at x equals, and it looks like 0 and 2, doesn't it? 0 and 2, because we don't have f double prime, so we need to use f prime. What happens at each of these? F prime changes from decreasing to increasing, from increasing to decreasing. So because f prime changes from increasing to decreasing, or vice versa, at those points. Now, you could also just be specific. You could say, because at x equals -2, f prime changes from decreasing to increasing, and from x equals, I'm sorry, that's 0, and at x equals 2, f prime changes from increasing to decreasing, if you want, but I'm all about efficiency, so one sentence does it for me. Find an equation of the line tangent to the graph of f at the point 0, 3. Well, let's just set up our normal tangent line. It's been a while since we've done one of these, but I think we'll be okay. It needs to be f prime of 0 times x minus 0 plus f of 0. So a couple blanks here, and we actually already know all of these answers. F of 0 is 3. They gave us that. But what about f prime of 0? Well, f prime of 0, that's the output on f prime. So essentially what we're building is 0 is the input. I want the output. 0 comma something. but f prime of 0, oh, we have the graph of f prime. How exciting. F prime of 0 means go to 0 on the x-axis and then drop down to the point. And the point here is a closed circle. There's actually a point, and it is the value -2. Now, if they had asked us for what is f double prime of 0, f double prime of 0, because there's a sharp point here, does not exist. F prime of 0 certainly exists. There is a point that is the existence of f prime of 0. Well, now that you've gotten the rundown here, you only have one more. Nothing too awful. Why don't you guys go ahead and try this one and then unpause when you're ready. Okay. This one just asks for points of inflection, so I'm just going to do a sign chart of the second derivative here, and we're going to kind of take our space from here. So it looks like we are going up here-ish and up over here. So I'm just going to do, that looks fine for my second derivative, yeah, something like this. Okay, and we're running from an x value of -1 over to an x value of 5. It's a weird looking 5. And this is the graph of f prime that we're looking at here. All right, critical points first. F prime is 0 at 1, and f prime is 0 at 4. Nice. Okay, and oh, I just said I was doing f double prime. Oof, I'm not doing great. Sorry, guys. Okay, f double prime. Oh my gosh. Erasing things, going back through. Very exciting. But I did a great job with f prime. F double prime. F double prime is created by looking at the increasing and decreasing of f prime. We increase until 1. Could have kept that 1. And it's a soft or a smooth curve there. So that's where f double prime is 0. And then we decrease until 3. Again, smooth curve. Nothing bad. And then we increase until 5. Cool. So we increased and decreased. So therefore, concavity, we are up, down, up, nothing to it. And then we just need some justifications. X coordinate of each, blah, 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 blah. Okay, so F has points of inflection at 1 and 3 this time. And I always use those curly braces to list things. We don't want to use brackets or parentheses because we use those for intervals. 1 to 3 because f prime changes from increasing to decreasing or vice versa. Right? Increasing, decreasing, or vice versa. Good. At, and I'm just going to rewrite this. By the time you write at those points or just rewrite that, it's pretty much the same, and that's a little more specific. Okay, let g be the function defined by g of x equals Steph. Find the equation for a tangent line. Yay, tangent lines. We should love those. We're so good at them. So tangent line, here we go. We're talking about g this time, so let's make sure we use g in this and not f. F means something different. So g prime of 2 times x minus 2 plus g of 2. This one could be a little trickier here. So let's start with g of x. So we know that g of x equals x times f of x. And so if I want g of 2, right, that guy up here, then that's going to be 2 times f of 2. What is f of 2? Well, this is f prime. That doesn't help. Oh, f of 2. They gave it to us up here. How exciting. F of 2 is 6. And that gives us 12. So filling in this tangent line, but leaving a space because I'll have to write in the spot for the slope, we know this is going to end with plus 12. Okay, what about g prime of 2? Before we find g prime of 2, we need to find the equation that creates g prime of 2, which is g prime of x. And that means I think we need a derivative. Ooh, an actual derivative today? How exciting. Don't forget, though, there are 2 functions multiplying together. So yes, we do need the product rule here. So 1, keep f of x the same, plus x the same, and then f prime of x. And so, when we find g prime of 2 here, it becomes f of 2 plus 2 times f prime of 2. Okay, and f of 2, we already found, we did that earlier, that was 6, plus 2 times, what about f prime of 2? Oh, wait, we have a graph again. How exciting. I think f prime of 2 is -1. So we end up with 6 minus 2, which is 4. Sorry about the bells. Obviously, I'm recording at school today, but that's okay. And we end up with a slope of 4. Look at that. We have our tangent line. And again, you can simplify your tangent line to slope-intercept form, but if you make a mistake simplifying, you lose the point for the answer, so I don't think there's really too much of a point in doing that, and I think we're good here. Such a common question. Oh my gosh, they love it. Here is the graph of f prime. Now tell us stuff. I think we also had a really nice conversation about how to use our calculators today. Super important, so make sure you're comfortable with all of that. I appreciate you joining me. Starting tomorrow, we start to see some of these applications now that we know how to do all of this. The applications are almost always going to start with f prime. Though tomorrow I'm going to backtrack on that because this is calculus, right? If they asked us about maxes and mins on the graph of f, you would just graph f and use your calculator to find the maxes and mins. We already knew how to do that after Algebra 2. Now we're taking it up a notch and saying, if you just have the derivative, can you find those maxes and mins? So thanks for joining me, and I'm excited to have you back next class.